In this lecture, I'm going to discuss the terms phase-locked and non-phase-locked and time-locked and non-time locked. So here's a little table. Let's start here. So here what I have in these black lines is simulated EEG data from 4 different trials and the average of those 4 trials. The gray line represents the envelope, so the time frequency power from whatever frequency I simulated this in. I don't remember anymore. Okay, so in this quadrant we have activity that is both phase-locked and time-locked. So time-locked just means that whatever is happening in the brain happens at a roughly similar time with respect to whatever you're calling time 0. So let's pretend that there was some picture that came on the screen here at time 0, and on every trial you can see that the dynamics in the brain are happening at roughly the same time with the same kind of temporal dynamics. So that's time-locked. And the activity is phase-locked when the phase angle time series, or the timing of the frequency band specific activity, is the same or very similar on every trial. And this is the key concept that is measured by intertrial phase clustering. Okay, so you can see in the trial average that you recover very nicely both the time domain signal and the time frequency domain signal. And in fact, this, when activity is time-locked and phase-locked, you will see it both in time frequency power and in the ERP, and also in time frequency intertrial phase clustering, although I didn't print that here. So now let's go to this cell. Here's when the activity is time-locked but non-phase-locked. So now if you look at the timing, you can see the overall time course of the dynamics are similar. So the, whatever sort of activation is happening with a similar timing after each trial onset. But the ERPs, the time domain signal, you can see that the phase angles differ over trials. And so that means that the exact timing of the ongoing, or that is to say the ongoing rhythmic activity is not really changing in its phase characteristics according to stimulus onset. So when activity is non-phase locked, then you can measure it with time frequency power, but not with the ERP. So the ERP is invisible to anything that is non-phase locked. And in this quadrant we have something that is non-time locked and non-phase locked. So now you can see the phases are different over trials, and the timing is also different. So in this trial, the dynamic starts earlier, and this trial it starts a bit later, and a bit later, and so on. So whether you can measure non-time locked activity in EEG really depends on how non-time locked it is. So in this case, you can see visually there's still quite some overlap. So we do get a somewhat dampened response, but still measurable with time frequency power, and we don't measure it with the ERP. Of course, if the activity was really strongly non-time locked, and the event in the brain was happening somewhere between 200 milliseconds and 2,000 milliseconds after stimulus onset, then eventually it's just going to average out and you wouldn't really see much of anything. Okay, so I and many other people like to call this activity phase-locked and non-phase locked. You will also come across the terms evoked and induced. So evoked would correspond to phase-locked activity, and induced would correspond to non-phase-locked activity. Personally, I don't really like those two terms because it doesn't seem very intuitive to me how evoked means phase-locked and something is induced, but it somehow requires it not to be phase-locked. I don't know. But the way I remember those is not by concept, because I don't get the concept to mathematical mapping of evoked to phase-locked and induced to non-phase-locked. I remember that evoked is what you can also measure with an ERP, and they start with the same letters. I don't know, whatever. Anyway, so I think this is pretty clear from this slide, the general idea. So let's talk a little bit about the math. In fact, there is no kind of universally agreed upon method to disentangle the phase-locked activity from the non-phase-locked activity. The method that I'll show you is fairly simple and straightforward, so I like it for that reason, and I think it's probably the most commonly used method in the literature for disentangling phase-locked and non-phase-locked. So we will distinguish between three terms. We have the total signal, the phase-locked part of the signal, and the non-phase-locked part of the signal. And so it makes sense that the total signal is just the combination of the phase-locked and the non-phase-locked part of the signal. And starting from this very simple assumption, we can do just a little bit of basic algebra and define the phase-locked part of the signal as whatever is left in the total part of the signal when you subtract away the non-phase-locked part of the signal, and vice versa for the non-phase-locked part of the signal. It's just the total signal minus the phase-locked part of the signal. All right, so here this is exactly the same text, just scrunched up here. So now one more assumption we have to make, which is that the phase-locked, or what we call what we measure as the phase-locked activity, is the time domain average, so the event-related potential. And taking this assumption, this allows us to quantify these different components of the signal and disentangle them. So we're going to call it the non-phase-locked part of the signal to be the total signal, so that's everything, and by everything or total I mean just the raw signal as you get it without changing it in any way. And we subtract the ERP from the raw signal, and that's what's going to give us our non-phase-locked component. Okay, so here's how this works. Here I'm showing a bit of data from two channels. Here this thick black line is the ERP, so this is the average of a bunch of trials, in this case 99 trials. And these two thinner lines show the single trial EEG data from one trial. And so here you see that one of them is the raw single trial data, so this we would call the total signal. And one of them is the same trial, but with the ERP subtracted. So here's the ERP, the thick black line, and then we take the gray line, that's the total signal, and subtract the ERP, and we get this, the thin black line. You can see they don't really differ that much, particularly at AFZ in this particular trial. They hardly differ at all. This is not so surprising when you look at the magnitude of the single trial activity versus the magnitude of the ERP. So the ERP tends to be about an order of magnitude smaller than the single trials. And so you're really just subtracting a relatively small part of the signal from each individual trial. So to compute the total power, you perform a time-frequency decomposition of each trial individually, and then you average the time-frequency spectra together. This is the kind of normal standard thing. This is what we have been doing so far. And this is, probably what, like 98% of time-frequency analyses in cognitive electrophysiology do. To compute the non-phase-locked part of the time-frequency power, you subtract the ERP from each trial, and then you compute the time-frequency representation of each trial and average together similar to this. So you start with the single trial minus the ERP, and then you go about your normal time-frequency decomposition just like you would for the total signal. Now once you have the trial average time-frequency responses for these two components, the total and the non-phase-locked, then you subtract the time-frequency response of the non-phase-locked component from the total component, and that gives you the phase-locked power. So I hope this is clear. We'll see this, of course, in MATLAB in a few minutes, so I think it will be more clear then. Okay, and so here we see some examples. This is from 01, I believe, channel 01. Here you see the total power, so this is everything, and here I have the ERP plotted on top, just so you can see how the time-frequency power kind of maps onto or does not really map onto the ERP. Here is the non-phase-locked power, so again, this was from the total signal. You subtract the ERP from each individual trial, and then compute the time frequency response again, and here you see the residual, basically the non-phase locked power. And it's already quite interesting that you see this early component really just disappears. It completely drops out. And where you see it is here in the phase locked power. And this map here is really just the difference of these two maps. So it visually confirms what you can already see here just looking at these two plots. So this is the sort of thing that you see fairly often in posterior channels and electrodes over visual cortex during a visual stimulus, that there is this very early kind of fast component that tends to be phase locked, and then there is later dynamics that tend to be non-phase locked. These later components really, almost by definition need to be non-phase locked. It's really hard to imagine how you could have some ongoing process that's non-phase locked to the stimulus, and then all of a sudden, many cycles after stimulus onset, it suddenly becomes phase locked. So most of the activity you'll see in EEG after 4 to 6 or 700 milliseconds is going to be all non-phase locked. Okay, so some people would say that this is a reflection of the ERP. That is, in some sense, partly true, but you can see there's also a lot more happening in the ERP than what you can really readily see in this plot. So I don't think it's really fair or accurate to say that the phase locked power is the ERP. There's more in the ERP than you would see just in this phase locked power. But they do tend to map on here. This is actually the time frequency decomposition of the ERP, so not of the single trials, but first average the trials together in the time domain and then take the time frequency decomposition, and that's what you see in this plot. Here's the intertrial phase clustering, and this tends to map onto the phase locked power most strongly. Okay. You might be wondering why you would want to do this analysis and why you would want to separate the phase locked from the non-phase locked parts of the signal and just disentangle that out of the total signal. To be honest, in my opinion, it doesn't really make a lot of sense in most cases to make this distinction. I don't think we really have a clear enough understanding of what happens in the brain that causes the difference between what we measure as non-phase locked versus phase locked. And these are all, perfectly, both of these components are perfectly valid measurements of what's happening in the brain. So I don't think it makes a whole lot of sense neurobiologically to disentangle these two plots. Mostly, I would say it makes sense if you have a more methodological question about whether something that you see or measure in the time frequency analysis can also be seen in the ERP. And so to disentangle, so to answer this question, then you need to get the ERP out of the data. You need to remove the ERP from the data. And then you can make a methodological point about whether something is present in the non-phase locked part of the signal versus whether it can also be measured in the ERP. Okay, so let's see. So now let's switch to MATLAB. There's very little that's new in this code. So it's mostly stuff that you've seen before, wavelet convolution and things like that. So it's the script is a little bit more complicated here, but that's just because we want to compute the time frequency representation of several different components of the signal. Okay. So you can run this first cell. There is really, I think, nothing new in this cell that we haven't discussed in previous lectures. There is this baseline time window for computing decibel normalization. And we haven't explicitly talked about this, although I've shown it before. If you still don't really know exactly what decibel normalization means or baseline correction means, then don't worry about it. We will talk about it explicitly in a future lecture. So for now, you can just ignore all these things that involve the baseline time. The rest of this stuff is pretty standard fair. Here we have the time frequency matrix, which is going to be frequencies by time. And you can see this first dimension has 4 elements. That's just going to be for the phase-locked and non-phase locked part of the signal. Okay, so now in this second cell, which you can run, I guess, but I would like to discuss some of this code first. Here we compute the ERP from this channel, and what is this channel? O1. So here we compute the ERP. This is just the time domain average over trials, which is the third dimension in EEG.data. So you can see that the ERP is a 1 by time vector. And now what we want to do to compute the non-phase locked part of the EEG is subtract the ERP from each individual trial. So each individual trial, we have 99 trials. So that gives us with leaves us with a matrix of time by trials, or 640 by 99. But the ERP is just one sort of trial length. So in order to subtract a vector from a matrix, here I'm using the function bsxfun. And the way this function works is we want to compute the subtraction. So this is like a function handle for subtraction. And we want to subtract the ERP from the data, which actually here is a 3-dimensional matrix because it's a 1, so 1 channel, 1 by time by trials. And this function bsxfun is going to figure out exactly how and how many times to replicate the variable ERP in order for it to be subtracted, the ERP to be subtracted from each individual trial. So bsxfun is a very useful function, and you can read more about it online. All right, so switching to the plots now. Here I have the ERP plotted. Here I have one single trial. I guess this is trial 10. And again, you see the total signal and the non-phase lock signal. They don't really differ that much. And again, this should make sense visually because the ERP is smaller in magnitude, so it ranges from like -3 to +7 or something, relative to the single trial data, which is an order of magnitude larger. Here I have the ERP again. This is the ERP from the total signal in blue, and the red is the ERP from the non-phase locked signal. So it should make a lot of sense that the non-phase locked ERP is 0. It needs to be that way by definition because we're subtracting the ERP from the data. So then when we compute the data, the ERP, it should be 0. Nonetheless, I think if you are doing this kind of analysis, it's always good to compute and plot the ERP from the non-phase lock part of the signal just as a sanity check, because if this were not 0, then something went wrong in this code, and you don't want to interpret any of the results any further. Okay, so now here in the next cell, this is the basically the same convolution code that you've seen before. It looks a little bit different here. It's a little bit more complicated just because we are looping over several different ways of extracting the or components of the signal for extracting a time frequency response. So that's why we need to compute the Fourier spectrum of the total signal, that's the data without changing anything, the non-phase lock part of the signal, and the ERP. And then you can go through this code line by line, but you will quickly recognize all of the important steps of convolution. And then, there's just some other special details that we have to take care of just to make sure that things are working. And then here a little bit below this, we're going to plot the results and produce a figure just like what we saw in the PowerPoint, using the function contour f to plot the data from each part of the signal. Okay, and then I just also wanted to quickly say here, so here we average the power over trials. Actually, this is for the ERP, so we don't need to average. Here we average over trials. This is the line where decibel normalization is taking place. And so you can look at that line if you want, but we will discuss it in more detail, both conceptually and mathematically in the future. Okay, so we can run that line. And here you see basically exactly what I have shown in the PowerPoint slide, although I think the panels are in a different order. I'm not sure how that happened. But okay, I believe that's it, actually. Yes, that's it. So I hope you enjoyed this lecture, and see you in the next one.